Now we're getting to something that's really fun and really exciting. We're going to learn about something called the pumping lemma. The first thing you should ask, of course, is what's a lemma? And a lemma is just, you can think of a lemma as a little proof or a little proof that you use to prove other things. So we're going to be doing a proof. We're going to be talking about the pumping lemma. We're not actually going to prove the pumping lemma, but then we're going to use the pumping lemma to do other proofs. And what kind of proofs are we going to use the pumping lemma to do? Well, so far we've said that some languages are not regular, right? You can try and make an NFA for them as long as you want, as many times as you want, but you're not going to be able to do it. Here's an example of a language I keep using, A to the N, B to the N, so a bunch of A's and the same number of B's. For any given N, it's a regular language, but if we say this is the language, so it's all strings that take this form over all values of N in the natural numbers, then we can't do it. And what we want to do is we want to prove that you can't make that NFA. Okay? It's not good enough to say, I can't do it. We want to prove it, and that's what the pumping lemma is all about. Okay. So before we get to the pumping lemma, we need to talk about some other stuff. Let's think for a minute about DFAs. Suppose we have a DFA, and why don't we just call it D, and it recognizes some language that we'll call L, right? So it accepts all the strings that are in L. And let's let S1 just be one string that's in L, okay? So there's some way to go through that DFA and figure out S1. And suppose this picture is part of my DFA, and I have to visit 3 states in this DFA to be recognized. So I visit this one, I transition, I visit this one, I transition, I get to here, this one's a double circle, and it says, yep, S1's in there. And my question is, how many letters are in S1 if I have to visit 1, 2, 3 states? And if you think about it for a minute, I hope you'll figure out that there's going to be 2 letters in S1, right? So for example, maybe S1 is the string AB, and I start at, maybe this is state 1, and I see an A, and this is state 2, and I see a B, and then I end up at state 3, which actually should have a double circle. So 3 states here, 1, 2, 3, but my string only had 2 symbols in it. Okay, let's talk about another string. We saw up here was our example where we said if we had 2 letters, we have 3 states. Now let's talk about the string S2. It's also going to be part of my language. It's accepted by the same DFA. So, maybe these 3 states were just part of my DFA, right? I didn't really draw the whole thing out. So suppose that S2 has to visit 4 states in the DFA in order to be recognized. How many letters are in S2? Well, if you think about it, we have to visit 1, maybe there's the start. We visit state 1, and then state 2, and then state 3, and then state 4, and we accept it at state 4. So maybe my string is A, B, B. So if we visited 4 states, 3 letters in my string. Okay? Suppose that instead of 4 states and 3 letters, I had to visit 27 states. I hope you see a pattern here, right? If I'm visiting 27 states in my DFA, then there's got to be 26 letters in my string. Okay, so what did we say? We said if I have 3 states that I visit, then we have 2 letters in my string. 4 states that I visit, 3 letters in my string. 27 states that I visit, 26 letters in my string. Now let's do it the other way around. Suppose that I have 17 letters in my string, then how many states do I visit? Well, if I have 17 letters in my string, that means I have to visit 18 states. If I have 34 letters in my string, of course, I'm going to visit 35 states. If I have 256 letters in my string, I'm going to have to visit 257 states, right? But the really important thing about this is we visit that many states, but some visits may be repeats to the same state, right? The DFA doesn't have to have 257 states. We just have to visit 257 states. So let me show you what I mean. Here's two different DFAs that both accept the string ABBA by visiting 4 states. So if we look at this first DFA here, right? When we take the string ABBA, we see the A, and then the B, and then the B, and then the A. So our string ABBA started out at state 1, right? Because we always start at state 1, right? That's the start state. So we started at state 1. Then we saw an A, right? So we saw that A, right? And after we saw that A, we went to state 2. From state 2, we saw a B, right? So we came along that arrow, and we ended up at state 3. We saw another B, and so we ended up at state 4, and we saw our final A that brought us to state 5, okay? So this particular string, ABBA, which had 4 letters, visited 5 states. Of course it was going to visit 5 states, and in this case, none of the states match up, right? But now, let's look at the second DFA down here. If I try the string ABBA again, on this one, I still start at state 1, and then I follow my A, so I end up at state 2, and then I follow my B, and I end up at state 3. But the next B, I go on this loop, so I'm still at state 3. And then I have an A, so I go to state 4. So in this second DFA, I have a 4-letter string. I visited 5 states along the way, but I repeated one of the visits. I visited state 3 twice, right? There's state 3 visited once, and there's state 3 visited twice. Okay. So I want to talk in general about some of the things I want you to think about. And what we're going to do is on the left-hand side here, I will give you kind of my general thoughts. And then to make it easier for you to understand, I'm going to show you a specific example. Now, this is just one specific example. I'm not trying to say that this example proves anything. I'm just trying to show you something so it makes more sense in your head. Okay? So let's get started. Suppose you have a DFA called D. Well, there's a DFA, and I called it D. Okay, so here's an example. This happens to be a DFA with 4 states, but I think it's a DFA, right? It's got start. We've got A and B outputs for each of the states. Okay, so specific example, but this is really what I want you to think about. All right, let's keep going. Suppose D recognizes a language. Of course it does. It might be the empty language, but it always recognizes something. And the language that we recognize is called L. All the strings that we accept are the set L. Okay. So take a second and just think about, for this specific example, what do you think the language is? Well, not what do you think. Figure it out. You can do it by now. What's the language that is recognized by this DFA? So I hope you came up with the language right here, right? So what have we got? We've got an A followed by a B, right? We accept the string A, B, and then we accept anything else that loops around here. So picks an A or a B and then keeps going, right? So starts with an A and a B, and then it can have as many more as you want of these A or B's followed by a B. Okay? Again, just for this specific example. In general, I want you to say, I've got a DFA, it's called D, and it accepts a language called L. Okay, I'm going to make an arbitrary call, and I'm going to say that whatever the number of states in my DFA is, I'm going to call that number M. Right? I'm just going to use M to represent the number of states in my DFA. So in this case, M is 4. Fair enough, right? How many states? 1, 2, 3, 4. M is 4. And let's let S be a string in D that has at least M letters in it, okay? S can be any old string that has M letters in it. So for example, here's a string that happens to be accepted by this DFA that has at least 4 letters in it. Actually, it has exactly 4 letters in it, right? At least means greater than or equal to M, right? So my string is A, B, 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 and I think you'll see that A, B, B, B ends up at state 4 and is accepted by this DFA, so that is a string that's in my language. Okay. Now, no matter what my string is, since it has M letters in it, it has to visit M plus 1 states, right? That's what we were doing for the first few slides, right? In this particular case, here's my string. It's A, B, 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 and it visits state 1. Then we see the A, we go to state 3. We see the B, we go to state 4. We see the B, back to state 3. See a B, go to state 4. Okay? But no matter what string we have, if the string has M letters in it, it visits M plus 1 states. So I guess since S has greater than or equal to M letters in it, it has to visit greater than or equal to M plus 1 states. And here I just happen to pick a string with M letters in it. Okay? Now, if I have M letters in it, and I visit M plus 1 states, so let's assume for a minute I have M letters in it and visit M plus 1 states. I visit M plus 1 states. I have M states, so there has to be some state that I visit twice, right? In this case, if I look at my specific example, I visit 3 twice, and I also actually visit 4 twice, right? Now you can imagine if I have more than M letters in it, I'm going to visit more than M plus 1 states. And so I'm going to have, you know, potentially even more repeats, right? Let's break apart this general example a little bit more, okay? Suppose I have some DFA, but I didn't draw it, okay? I put this cloud in front of it. There's actually some circles and arrows in here, but you can't see them because they're covered up by this cloud, okay? And the language that's accepted by this DFA is some set, but I'm going to put the language in here, right? It's just hidden by that starburst, whatever that thing is, okay? Let's assume that we still have 4 as the number of states in this DFA, even though we can't see those states, okay? If I have a string that has 4 letters, it's going to visit 5 states, right? And I'm just going to say, let's say it visits state alpha, then beta, then gamma, then delta, then epsilon. Okay? Let's just say it visits those, right? So maybe alpha is state 3, and beta is state 1, and gamma is state 1, and delta is state 3, and epsilon is state 2. Or, you know, maybe alpha's 1, and beta's 1, and gamma's 2, and delta's 1, and epsilon's 2. I don't know, right? All I know is that out of these guys, each of these represents a number, right? So alpha is the number of one of the states. Beta is the number of one of the states. It may be the same as alpha. Gamma is the number of one of the states. It may be the same as beta. It may be the same as gamma. As alpha. But whatever we do, I'm guaranteed that at least 2 of these Greek letters have the same number. They refer to the same number. Okay, so here's a theorem that I'm not going to prove, but I think that if I argue it for a little bit, you'll understand and you'll believe it even though I haven't proved it. Really, I should prove it to you, but I don't want to take the time to prove it, so I'm just going to give you an outline of the proof, okay? And here's my statement. If a DFA recognizes an infinite language, then my DFA must have a loop in it. Remember that by definition, our DFAs have to have a finite number of states. So we've got a finite number of states, but we're recognizing an infinite language. There must be a loop in it. So let's try and argue this. Here's my statement again. I just rewrote it. Okay. Let's let D be a DFA that recognizes some infinite language L. Okay, so I'm just calling it D. And let's suppose that D has M states. I don't know what M is, but D is a finite number of states, and let's just, whatever it is, if it has 56 states, then M is 56. If it has 72 states, M is 72. Okay? Now, my language is infinite, right? If it's an infinite language, then I can pick any number. Let me pick the number 72 or the number 648. Whatever number I pick, I can always find a language that has more than that. I can always find a string in my language that has more than that many characters, right? If I pick the number 72, it's an infinite language. I'm going to have at least one string in there, lots of strings, an infinite number, that have more than 72 characters in it, right? If I pick the number 1250, there's a string in there that has more than 1250 characters in it, okay? Okay. So we said D has M states. And we also know, because of the stuff that we've been looking at, that if I pick a string that has at least M letters in it, then that string visits at least M plus 1 states. But hang on. We said there were only M states on the previous slide, right? So I must visit a state twice. But if I visit a state twice, the only way I can do that is if there's some loop in my DFA, right? I mean, the loop might be a loop that's on its own, that takes me back to the same state I was in. It might be a loop that takes me back. It might be a loop that takes me all over the place to here. But somehow there's a path through my DFA that lets me repeat. Okay. Now I'm going to show you a weird procedure. All right, don't try to totally understand why we're doing this right at first. Basically, we're going to play with DFAs. We're going to think about loops. And what I want you to know is I'm going to show you an example, right? Again, I'm just showing you an example so you get a feel for this in your gut, and then we'll talk about the more general case. But I'm going to show you a DFA that has 5 states. And I'm going to pick strings to look at that have at least 5 symbols in them, right? At least 5 letters in them. And these are strings that are accepted by my DFA. So if the DFA only has 5 states, but I have 5 symbols, remember 5 symbols means I visit 6 states, so we must have some sort of repeats. Okay? Now, what I'm going to do in this weird procedure is I'm going to split the strings into 3 pieces. I'm going to call the pieces X, Y, and Z. Okay? Just because that's what everybody does. Okay? But I'm going to split the string into 3 pieces that's totally based on how the repeats happen. And just stick along. I'm going to show you a bunch of examples of how I'm going to do this split, and I think you'll understand what's going on afterwards. Just pay attention for now. So here's my first example. There's a DFA up at the top. Nice DFA. And it does have some accept states, right? State 2 and state 4 accept states. And I have this string A, B, C, B, A. I start at state 1. And let's see, after I see the A, I go to state 2. And after I see the B, I go to state 3. And then I see the C, so I'm back at state 2. I see the B again, so I'm at state 3. I see the A, and I'm at state 4. Okay. Alright, so there it is neatly. So here's my question, and it's actually not too hard to answer, right? What's the first state that we visit twice? So if you just look at the visits, the first state we visit is 1, then we visit 2, then we visit 3. Oh, look, 2, that's a repeat, right? So, 2. Alright. Now what I'm going to do is I'm going to split my string into 3 pieces by drawing a line through the repeated state. So I'm just going to draw a line through the 2's. Okay. A little bit neater. And I'm going to call the first section, the letters that come before the first line, X. So I'm going to call this part X. In this case, X just equals the letter A. I'm going to call this second piece Y. So Y is going to equal the string BC. And I'm going to call everything after the second line Z. So in this case, Z is just going to be BA. So there it is, a little bit neater, right? X is just the string A, Y is the string BC, and Z is the string BA. Okay, that was easy. Let's do it again. Okay, I changed my graph slightly because I wanted to show you some things, so it doesn't really matter. I'm just using a different DFA. DFA still has 5 states, but I just wanted to show you how I changed the DFA a little bit. Okay, so here's my string, A. Let's see, we start at state 1. We see an A, we go to state 2. We see another A, so we stay at state 2. We see another A, so we stay at state 2. We see a B, so we go to state 3. And we see an A, so we go to state 4. By the way, notice 5 states in my DFA, 5 letters in my string. I knew there had to be at least one repeat. In this case, it looks like I have a bunch of repeats, right? I guess that's 2 repeats, right? I started, did a repeat, did a repeat. All right, there it is, looking nice. All right, so my first repeated state is this, are these 2 2s, right? And yeah, I have more repeats, but all I care about is my first one. So I draw some lines through it, and I split it into X, Y, Z. So in this case, X is just the string A, Y is just the string A, and Z gets the mega string ABA. Let's do another example. Here's a string that is certainly at least M symbols long. It's even more, right? So my DFA has 5 symbols. This string has, what do we got? We got 1, 2, 3, 4, 5, 6, 7, 8. 8 letters in it. That's fine. 8 symbols in it. So let's just go through this. We start at state 1. We see a B, so we're still at state 1. We see another B, so we're still at state 1. We see another B, we're still at state 1. Finally, we get interesting. We see the A, we're at state 2. Now we see a B, we go to state 3. Now we see a C, so we're at state 2. Another B, so we're at state 3, and an A, and we're at state 4. So there you go. And the first repeat in this case is the first 2 states we visit. That's fine. We draw our line. And now this gets interesting, right? Because X is actually equal to lambda. Y is a string with just 1 character in it, and Z is fun. Z is B, B, A, B, C, B, A. Okay. There you go. All right. Let's do another. I'm going to have the string A, B, C, blah, blah, blah. So let's start. We start at state 1. I see an A, we go to state 2. I see a B, we go to state 3. I see a C, back at state 2. I see a B, state 3. I see a C, we're at state 2. I see an A, we're at state 2. I see another A, we're at state 2. I see a B, we're at state 3. I see an A, we're at state 4. Okay, so there it is written out neatly. There's our first repeat, right? We looked and we said, what's the first state that I visit that I see again? So I saw a 1, haven't seen that yet. See a 2, haven't seen that yet. See a 3, haven't seen that yet. Oh, look, there's a 2. We've seen a 2 already, so I circled the 2s. Draw lines and do my split. So X is A, Y is BC, and Z is BC, A, B, A. Good enough. All right, I'm changing the DFA one more time just so I can show you something interesting. Really, I'm just highlighting this so that you can see that I've changed it. Okay, so let's see. We start at state 1. We see an A, so we go to state 2. We see a B, so we're at state 3. A, so we're at state 4. Another A, so we go to state 5, and a C, so we go to state 4. So there's your first repeat. Okay, there it is, drawn a little bit more neatly, but again, the first repeat is these 4s. And just so if you're looking at the slides separately, you can see this. First repeat looks good. So let's just review how we did our slices. In this case, looks like x equals ABA, y equals AC, and z is just lambda. So again, z is lambda. Okay. So now I think you've seen enough examples of this that we can go on. And let's just think about some general questions again. Let's suppose our DFA has m states. And here's the first question I have for you. Can you have a string with fewer than m-1 letters go through a loop? And somehow I managed to put the answer right here. But yeah, I think this is an example, BBA, right? It's a string. We have 5 states. Here's a string with 3 letters, and I think to do BBA, we go through a loop, right? BBA. So, yes. Okay, now suppose a string accepted by our DFA has m letters, and our DFA has m states. Do we have to go through a loop? And I hope you're convinced that, yeah, we do. Right? Remember this slide, right? If m was 4 and we had 4 letters in our string, that meant we visited 5 states, so by the pigeonhole principle, 2 of them had to be the same. Okay? Now, if we always use this weird method to split up our paths, right? So we have a path, and we pick the first repeat, we do the split just like we've been doing. And we've seen a case, if you go back, you'll see that we had one example where x was equal to lambda. And we've had another example where z was equal to lambda. And here's my question. Could y ever end up being lambda? So think about that for a second. And I think what you'll figure out is the answer is no. And here's why. The way we got the y part was by drawing these 2 lines, right? Y is what's ever in between those 2 lines. And the 2 lines have to be in different spaces, right? They could be right next to each other. So maybe instead of the 2 lines being there, we could have had, we could have had one go through this one and one go through this one. But that's as close as they can get. The 2 lines can't be on top of each other, right? So whatever we do, the 2 lines, because of the way we did it, we said, where's our first repeat? You have to have a repeat. So there's our first number, and there's our second number, right? There's the second time we see the same number, right? And we draw the lines. So it's possible the second time we saw 2 could have been there, but that's as close as you can get, right? You can only, your 2 lines, there has to be a letter in between. So the answer is no. Y can never equal lambda, just because of the way we defined this, right? I just picked a really interesting way to do it so that y could never equal lambda. Okay. So here's another question for you. Is the string x, y, y, z in the language? Right? So in this case, let's just look at this example up here for a minute. X is equal to A, right? And y is equal to BC, and z is equal to BC, A, B, A. So I'm asking whether x, y, y, z is in my language. I mean, you know, x, y, y, z, that would be, first I have an A for x, then y is a BC, and then another BC, and then whatever z was, well, z had a BC in it too, but then it's A, B, A. Right? But I have my x piece, my y piece again, and then my z piece. Right? And let's see, is this one in there? Well, we've got A, B, C, B, C, B, C, Where's the A go? A, B, A. And sure enough, that one's in my language. But if you think about the more general case here, the Y piece always has, the Y piece always has the same number on these lines, right? So that means I started at 1, then I went to 2, then I did some stuff, I got back to 2, and I did some more stuff, right? So this in-between bit is kind of some steps that I take that start and end at the same state. So if I do stuff that gets me to state 2, then I hang out in state 2 for a while, and then I do stuff that leaves state 2 and continues. Well, I think I can do this piece as many times as I want, because I could go to state 2, do the BC, I'm at state 2. Let's do BC again, I'm still at state 2. If I do BC again, that'll still take me to state 2. Okay? So, yeah, I think X, Y, Y, Z is in the language. And furthermore, I think that X, Y, Y, Z is in the language no matter what DFA I have. Right? Because if you think about it, you know, wherever Y starts and ends, it's always the same state. So you can imagine that, like, the X part has me following a path through my DFA, right? So I just visit a bunch of states that I take a path. But whatever I do, I end up at this special state because the X part takes me there. The Y part takes me on a journey somewhere that ends up back at this state, and then the Z part keeps going from there. So, you know, if I want to, I can just keep bouncing around, right? So I take my X path, I take my Y path once, and instead of going down on the Z path, I take my Y path again. And I take my Y path again, and I take my Y path again, and eventually I say, all right, I'll do the Z part now. Okay? So if X, Y, Z is in my language, then yep, X, Y, Y, Z is in my language, but so is X, Y, 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 Z. Yes. Okay. What about X, Y to the 517Z? Sure. Absolutely. So again, I mean, if the X part of my DFA, right, the X path through the DFA, right, is taking me on here, so this kind of covers the X piece. And then the Y piece starts here, takes me on a little journey, but ends up back there, right? That's the Y piece. And then the Z piece continues me on from here and takes me somewhere else, right? Then, if I want to, I could just take the X path, right? Dum-de-dum-de-dum. I can take the Y path as many times as I want. If I'm bored, I could take it 517 times. Right? Pretend that's 517. But eventually, I always end up back here, and so then I can do my Z bit. Right? Because that last little bit represents what I do for Z. Okay, so here's another question for you. Suppose my DFA has 5 states, right? Like our example here. What's the maximum length of the string where I concatenate X and Y together? So in this case up here, we've got X is just an A, and Y is a BC. So XY together is the string ABC, so the length of XY is 3, right? I want to know, how big can XY get if it's at its biggest? Well, let's look at this example. Suppose my string is 5 letters long. And let's suppose that this is what my string is. It's some letter followed by another letter. I don't know what letters. I'm not going to tell you what letters. But it's five letters long. And I'm going to visit these 5 states. Again, I'm not telling you exactly what 5 states they are, but they're the ones I'm going to visit. So I'll visit alpha, then beta, right? So I'll visit alpha, I'll see this letter. I'll visit beta, I'll see this letter. I'll visit gamma, see this letter. Visit delta, see a letter. Epsilon, see a letter. And I'll end up at state zeta. And the question I have is, where is the absolutely last place I can make my second cut, right? So in other words, where do I have to have a duplicate? If, I don't necessarily have to have my, alpha and beta don't have to be the same number, right? They could be different numbers. But I only have 5 states in my DFA. So forget where the first cut is. By the time I get to this zeta, there's got to be a cut there if there wasn't a cut before, right? That one here has to be my second cut, right? Because this one has to be a repeat if nobody else has been there. So the maximum, right, so that if that's my second cut, right, that means that Z, the Z part's over here, and the XY is these letters, right? So in this case, Z would be the empty string, and XY is whatever letters these are. So the maximum length of the concatenated string XY in a DFA with 5 states, and if my string has 5 letters, is 5. Now, was it important that we talked about a string with 5 letters? If we had more letters in the string, right? As long as my DFA has 5 states, no matter what, my first cut can be any of these first 5 things, right? Because each of these could conceivably be a different number, right? It could be state 1, 2, 3, 4, 5. But when I get to this last one, if I haven't made 2 cuts already, I have to make 2 cuts. So even if my string has 5,000 letters in it, right, XY has to be at most 5 characters. It could be fewer than 5 characters, right? So for example, maybe my cuts are on alpha and beta. Maybe they're the same number. So XY could have just 1 character in it, right? So in this case, let's see, X is lambda, Y is whatever this character is, and Z is the rest of this stuff. So in this case, if my 2 cuts go in the first 2 spots, then the length of XY is going to be 1. But that wasn't my question, right? My question was, suppose I have a string that has greater than or equal to 5 letters for my DFA with 5 states. What's the maximum length that XY could take up? And the maximum length is when I make these cuts, because even if I have more letters out here, the first repeat's going to happen by there. And so that means the maximum length when I take the X and the Y part is going to be 5. Right? Because in this case, the X part doesn't have anything in it, right? So the X part equals lambda, the Y part equals all these question marks, and the Z part is everything else. But when I say how long is the X and Y, well, 0 plus 1, 2, 3, 4, 5. It's 5 characters long. Okay, so can you make the jump? If our DFA has M states, and we have a string with, let's even say, greater than or equal to M letters, I think the maximum length of the concatenated string XY is going to be M. And I hope you agree with me. So let's just keep going. What do I mean by this notation, right? Well, that's just the size of X, the length of X plus the length of Y, right? That's a notation that we reviewed at the very beginning of the course. But so the length of X plus the length of Y is the same as the length of XY, right? So could the length of X plus the length of Y ever be longer than M? And the answer is no. I hope you're convinced, right? Because if our DFA has M states, then the length of X plus the length of Y, that's just the length of XY, right? Which the biggest it can be is M, right? If the biggest it can be is M, then we could say this statement, right? So this is where I was actually trying to get to, is I want you to agree that if I add up the number of letters in X and add up the number of letters in Y, no matter what I do, that number of letters is always going to be less than or equal to M. At most, there's going to be M letters. Okay? So, let's assume that we have M states, we accept a language called L, and let's pick a string, some string that's accepted by our DFA, and that has at least M characters, right? So greater than or equal, so here I've got my string, and my string S is an element of my language, and the length of S is greater than or equal to M, right? At least M characters. So, we know that I could also write my string as X, Y, and Z concatenated together, right? We know that the length of S is greater than or equal to M, And we know that if I add up all three of these guys separately, I also get something greater than or equal to m, right? Because how long is the length of x plus the length of y plus the length of z? Well, that's just how many letters in x, how many letters in y, how many letters in z, and all those pieces together make s. Okay, so we haven't proven this, but I hope I've convinced you that if I have a DFA, it has m states, accepts sublanguage L, and if I pick a string that's accepted by my DFA and has at least m characters, right, so greater than or equal to m characters, that tells me that the number of characters in my string is greater than or equal to m. We also believe, we haven't proven it, but we believe that the number of characters in just the x and y part has to be less than or equal to m. And with that, we can do something really cool. So this is really cool and kind of really sneaky in a roundabout way. It's kind of a good hack, I think, okay? Here's how we're going to prove a language is not regular, all right? If we have our language L, what we're going to do is we're going to say, sure, I'll assume L is regular. And then we're going to pick some string in L whose length is greater than or equal to m, right? Doesn't matter what string we pick. No matter what string we pick, we can split that into an x, y, and z part, right? And then what we're going to do in step 3, we call it pumping if we stick a bunch more y's in, right? So x, y, y, z, or x, y, 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 z, right? Or even, actually, we can also take out y. We could say xz, right? I hope you can convince yourself of that. Maybe go back and look and see that, you know, if x takes us to a state, y goes around for a while and ends up back at that state, and z takes us away, then we could just get rid of the y too, right? So we call pumping when we mess with the y part. And we're going to show that our string, we pick just one string, and we're going to show we can't pump it. Right? You can't keep adding the y parts to it. But the pumping lemma tells us we can. So we say, oh, I've got a contradiction, so it must not be regular. Okay, so here's the formal definition of the pumping lemma for regular languages that you'll find in the book. It's a little bit more complicated than what we've been talking about, but I think you'll get it given what we've been talking about. All right? So L is an infinite regular language over the alphabet A. And if L is an infinite regular language over the alphabet A, then there's some number, m. Pumping lemma doesn't say, oh, m is going to be that number of states in the DFA, but trust me, m's the number of states in that DFA. Such that for any string s, where s is in my language, and it's also the case that the length of s is at least as long as m, right? And we need to be at least as long as m. Why? Well, you know why, because we need to have some double. Well, if we have that, then we can split into x, y, and z, right? X, y, and z have to be strings that are in my alphabet, right? We're being very general here. Y isn't empty. And s is concatenating x, y, and z together. The length of x, y squished together has to be less than or equal to m. And whatever k I pick, x, y to the kz is in L. Okay? So this is the formal definition of the pumping lemma for regular languages. Let's see how we use it. Okay, all our proofs using the pumping lemma are going to be using proof by contradiction. We talked about in the very first week of class. But just to remind you, how do we do proof by contradiction? We assume we've got some fact F. It's true. We do a bunch of smart things that lead you to a contradiction, right? And we draw it like this. Remember, it looks kind of like 4 arrowheads hitting together. Like, after we do all our great stuff, we discovered that the moon is made of green cheese. But the moon is not made of green cheese. But it has to be. But it's not. But it has to be. Well, the only way we could decide that the moon is made of green cheese is if something we did earlier in our proof is wrong. And the thing that we did earlier in our proof that was wrong was our assumption, so therefore F must be false. Okay? That's the outline of a proof by contradiction. Please, 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 if you don't remember more about them, go back and look at the first set of slides. Let me start by just giving you an outline of a pumping lemma proof. We're not going to do it perfectly yet. I'm just giving you an outline. Okay. Let L be a language, right? In this case, I want to prove that the language a to the n, b to the n, where n is any natural number, is not regular. So what strings are in my language? Well, it has lambda, it has AB, it has AA, BB, it has triple A, triple B, and so on, right? So let's let L equal this language, and now we're going to make the key assumption that's going to help us with our proof by contradiction, all right? We're going to assume L is regular, okay? So if L is regular, then we can make a DFA to recognize it. So there's some number M, we don't know what it is, but there's some number, right? It's just going to be however many states in our DFA, but there's some number M for which the pumping lemma applies, okay? In particular, any string that's in my language that's at least M characters long, we could split up into our X, Y, Z. Y is not the empty string, right? Y doesn't equal lambda, and these things are true. So, if this is the case, the pumping lemma tells us this is true for every single string in lambda. Sorry, in L. Every single string in my language. If we can find just one example that it's not true for, we've got a contradiction, and therefore our assumption must be false. L must not be regular. Okay? So let's do the real proof now. Okay, and we're just going to go through it step by step. So we start, let L equal our language, and assume that L is regular. There's our assumption. Well, let's also assume that M is the number from the pumping lemma. And now we get to pick any string we want. Any string we want, right? As long as it has at least M characters in it. The string I'm going to pick, and I'm picking it because I know it works for this. We'll talk later about how to pick a good string, but I'm picking this one because I know it works. All right? And I'm going to pick the string A to the M, B to the M. So, just review. Let's suppose that the DFA that recognizes this language, right? I'm pretending there is one. Let's pretend that the DFA that recognizes this language has 5 states in it. Then I would be picking S to be 1, 2, 3, 4, 5, 1, 2, 3, 4, 5. Right? Oh, but maybe it doesn't have 5 states in it. Right? Maybe it has 7 states in it. Well, that means that M is 7, so my string is going to be A to the 7, B to the 7, which is 1, 2, 3, 4, 5, 6, 7 A's, and then 1, 2, 3, 4, 5, 6, how many do I have? 1, 2, 3, 4, 5, 6, 7 B's, right? So in that case, this is what S would be, right? I don't actually know what M is. Well, actually, I know M doesn't exist, right? Because L's not regular. But let's pretend it does for a minute. Maybe, you know, for all we know, M is 753. So that means my string is A to the 753, B to the 753. So there are 753 A's in a row followed by 753 B's in a row. Okay? But whatever's the case, no matter what is the case, we're just going to let S equal A to the M, B to the M, whatever the M is. Okay? Now, whatever I picked for my S, A to the M, B to the M, that's certainly in my language, right? Because here's what my language is, and A to the M, B to the M is in this language, so that's a check. And the length of S is greater than or equal to M. Well, sure it is. How long is S? It turns S has 2 times M letters in it, right? Because it has M A's, right? A, and there are M of these, and then BB, however many. So how many letters total? There are 2 times m. So if there's 2 times m, well, I know that 2 times m is greater than or equal to m, so that's true. So the pumping lemma applies. Now, by the pumping lemma, we can split our string into an XYZ part, where we know for sure y isn't lambda, and we know that if I squish the x and y part together, the number of letters in that is less than or equal to m. Okay? Given that the xy part is less than or equal to m, that means the xy part must just have a's, right? Because remember, I had a bunch of a's, right? Followed by a bunch of b's, right? And there's m of these and m of these. So if the number of letters in xy is at most m, then the biggest xy could be is all these a's, right? So xy has to just have a's in it. Now, you can say, boy, that's lucky, or you can say, boy, Dr. K picked a good string. Okay, so we know that xy is just a's. But if the x part is all a's and the y part is all a's, y has to have at least one a, maybe more, because we know y is not lambda, y is not the empty string. So let's just say, I don't know, y has k a's in it. I don't know what k is, but you know, y has either 1a or 2 a's or 5 a's. K is however many that is. So y, you know, if k is 3, y is a. And if k is 5, y is 5 a's, and so on. Okay. We know by the pumping lemma that x, y, y, z has to be in L, right? That's just the rule. We take our x, we put 2 copies of the y, we put z, whatever those pieces were, that's in my language. Okay. Let's just pause for 1 second and let's think about what x, y, y, z is in this case. Okay? So, we know that s is the string a to the m, b to the m. And we know we're splitting up s into x, y, z, where y isn't empty, and the xy part has no more than m letters. So, you know, I don't know exactly what it looks like, but, oops, sorry. But here's my bunch of a's, and here's my bunch of b's, and, you know, I make that magic split, and maybe the split happens here. So, that's my x bit. That's my y bit, and that's my z bit, okay? So, what do we know? We know that my y bit is all a's, right? So that's what this piece says here. Y is a bunch of a's, however many it is. X also has to be just a's, right? And what's z going to be? It's going to maybe have some a's and then all the b's. How many a's is it going to have? Well, if there are m a's all together, and x has q of them, and y has k of them, then z gets start with m, subtract off k, subtract off q. So z has this yuck in it, right? It has this many a's, and then this many b's. Okay, so we know that's what y is, we know that's what x is, we know that's what z is. So what's x, y, y, z? Well, let's just make this piece bigger so I can show you, right? My y is a to the k, my x is a to the q. Here's what my z is. So x, y, y, z, I take x is a to the q. There's my x piece. I take my first y, which is a to the k. There's a y. I throw in another y, which is another k a's, right? These are both my y's. I throw in a z, right, because it's x, y, y, z. So here's my z, which is this yuck. And now I just do the math. I have, let's see, q plus k plus m minus k minus q a's and m b's, so that's this thing. And let's see, if I start with q and I subtract off q, and I start with k and I subtract off k, we end up with m plus k a's and m b's. Okay? So x, y, y, z is this, right? X, y, y, z equals a to the m plus k. So we have whatever m plus k is a's followed by mb's. All right, so we're back to our proof, right? We left off here, right? We're trying to figure out what x, y, y, z was, but now we know. So let's pretend that we pasted all our math we did in here. We don't have enough space. But x, y, y, z is this, right? And we know that k is greater than 0. We know that, right? Because we saw it in our math. Go back and look. But hang on. Here's what x, y, y, z is, right? X, Y, Y, Z is a string that has a bunch of A's, followed by a bunch of B's. But how many A's? Well, first there's K of them, and then there's another M, but there's only M B's. But my language says I have to have the same number. But my string doesn't have the same number. So my string is not in this language. But wait, the pumping lemma tells me my string has to be in this language. But wait, my string's not in the language, but the pumping lemma tells me it has to be, but it's not. We have a contradiction. So notice I drew, oops, sorry. I drew the nice contradiction symbol. So our assumption must be false. What was our assumption? We assumed L was regular. We were wrong. Thus, L isn't regular, QED. We're done. Now here's what I call my plug and chug outline of a pumping lemma proof. Okay? Here's how you can do any pumping lemma proof for regular languages. You start and you write, let L equal, and whatever your language is, you write it there. And then you write exactly what it says here. Let M be the number from the pumping lemma. Let S equal, now you got to put something smart in here. Okay? But you always have to make sure you say, look, S is in my language, and the length of S is greater than or equal to M. Then, by the pumping lemma, X is splittable into X, Y, Z, where Y is not empty, and the length of X, Y is less than or equal to M. Now you do some math. And you say, by the pumping lemma, and now you say something about what happens if I add y's, what happens if I take away y's. And you say, wow, I have a contradiction. So L is not regular, and then you write QED.